Okay, so let's take a look at what we have left for the rest of the semester, what chapters we got to go through, and what our time frame looks like. We're entering into week 12, so we essentially have 6 weeks left, not minus Thanksgiving. It's a 16-week course, and they do not count off for the week that we're gone for Thanksgiving. So just prepare yourselves. You'll have a little bit of homework over the Thanksgiving break. We're finished up with chapter 7 and 8, so it's time for the next homeworks and the next set of the tests. And so I will have the homeworks up today, maybe even by midday, depending on how things go, maybe not. But the chapter 7 and 8 and test is going to be next Monday, a week from today. So you got a week to get the homeworks done. They're going to be due then. If you need a little extension on the homeworks, that's fine, but make sure you let me know and do be kind of working on them because the homeworks are going to help you out on the test for sure. So chapter 7 and 8 homeworks and tests are going to be Monday. We have 2 weeks until Thanksgiving. So the Thanksgiving break, this is 23rd through 27th. We should be well through chapters 9 and 10 by then. We will probably do a break and a test for those two as well. I'm not going to give you a test over the Thanksgiving break, but we might have it kind of right when we get back because we're going to be able to go through these pretty quickly. I got more than halfway through this chapter 9 today in first period. So we have oceans and then restless oceans in motion. And then we get into our weather chapters, and you can see that the last 4 chapters that we have, because we've already done 15 and 16, we did those at the beginning of the year. The last 4 chapters, 11, 12, 13, 14, are all basically different things about the atmosphere. You have our atmosphere, you have moisture in our atmosphere, you have atmospheric motion, and then you have weather patterns, which is more atmosphere. And so they do spend a lot of time talking about the atmosphere and the air. We're going to go through them rather quickly, but that's going to be after the break. So I think what we're going to do is I'm going to have the homeworks up for 7 and 8. We're going to take the test next Monday. We should get done with chapter 10 sometime that week. It should be. It might even be early that week. I'll have the 9 and 10 homeworks up as well, which you can work out on over the Thanksgiving break. When we get back, we should be kind of into the weather chapters, and we will essentially have 2 weeks once we get back. We're going to go through the weather chapters. We'll probably take a test, maybe that 7th here. Yeah, turn it off and put it in your backpack. The 7th here, and we have 2 more things to do before the final exam. We have the SLO test, which is going to be, it's not a test grade. It counts as like one of your lab grades, I believe. I'll have to look at the syllabus. But it's a multiple choice review for the test. It's basically like a version of the final exam with less questions on it. But it goes over all the different chapters and the things that we've done and probably has final exam questions right on it. We will also do the the signature assignment, which will essentially be a weather lab that we will kind of do together. Since I've been teaching this, I haven't had a whole lot of luck with just letting y'all just go at it because it's really vague. And so you need a lot of kind of instruction and leading through it. So we will kind of work through that together, or at least I will show you everything that you need to do, and then you just have to duplicate it. But that on this one, we're going to show you a bunch of different informational weather maps, and you will actually create a weather map like you would see on the news. I think it's pretty neat. But that's what we're going to go through the atmosphere and the weather chapters kind of all together into one lump sum and one final test, 11 through 14. And then towards the end of this week, I don't know exactly what day. I'll have to look and see what the final day of the semester is, but we will take our final exam right at the end there, and then we'll be done, and we'll have a week of class or a week of high school class days that are not college class days. So if y'all would like to do anything then as a class, that's up to you, as long as you're following the rules of the school. Other classes have had like a a little like potluck. I don't know if we can do a potluck party. So maybe no potluck party, but other classes have brought like a Switch and had like a game tournament, or yeah, if y'all want to do like an Among Us tournament or something. Yeah, whatever. I mean, y'all can even have different things that you do in different groups. And obviously, it's a whole week, so we might just have days where y'all just do your own thing, and you'll have other classes that you might need to study for final exam time. But just be aware that that last week, you have some opportunities to do some interesting things if you would like. So we're going to go ahead and get started with the PowerPoint today and talk about oceans, the last frontier, which that's not that. It's still a frontier. We haven't fully explored all of the oceans. It's not the last one. Space is the final frontier.
I just watched all the Pirates of the Caribbean, so I feel pretty ready.
Oh, did you? Nice. Yes.
Go to the library. It's just somewhere on my Chromebook.
Yeah, you can go. So they start off by basically saying Earth is referred to as the blue planet, which we all know. The reason it's referred to as the blue planet is because we have a lot of water. 71% of the Earth's surface is oceans and marginal seas, compared to only 29% continents and islands. And they even kind of hammer this home by showing you the pole views of the Earth. The northern hemisphere, and no one really refers to them as this, but the northern hemisphere is called the land hemisphere. The southern hemisphere is the water hemisphere. And if you look at it top down from the North Pole, you see quite a bit of land from this view. If you look at it bottom up from the South Pole, there's actually very little land. Now, this is kind of skewed because it marginalizes and doesn't show the best view of the land that's actually at the equator. So it's not like the southern hemisphere has very little land. Just relatively, you've got Australia over here. You have the southern tip of Africa and most of South America. And then you have Antarctica, but that's it. Where the northern hemisphere, you have all of Russia and Europe, the majority of Africa above the equator, all of North America. And so you do have quite a bit of land from the northern hemisphere versus the southern hemisphere. That being said, don't think that anybody actually refers to the hemispheres that way. It's just an illustration kind of thing. So we have 5 main ocean basins. We have the Pacific, the Atlantic, the Indian, the Arctic, and the much forgotten Southern Ocean, which maybe should be called the Antarctic Ocean. I don't know. But yeah, the Southern Ocean is what we call it. A couple things about these. The Pacific is the largest. The Atlantic is second place, about half the size of the Pacific. The Indian Ocean is slightly smaller than the Atlantic. And the Arctic Ocean is tiny, and the Southern Ocean isn't that large either. So 7% of the size of the Pacific Ocean for the Arctic Ocean, and then the Southern Ocean encircles Antarctica. Know that some of these have very definite boundaries. Like, we obviously know where the Pacific Ocean begins and ends because it has continents that border it. Same thing with the Atlantic Ocean. With the Southern Ocean, it kind of has an arbitrary line that we draw around it to say this is the Southern Ocean versus any of the other ones that it borders. And then the Arctic Ocean, they don't even, on the next map, they don't even bother putting a line. So it's kind of hard to know exactly where the Arctic Ocean begins. It could just be the Arctic Circle. It could be anything like above Europe and Russia up here, and above Canada. I don't know if it goes all the way down to the southern tip of Greenland. I don't know. I'll have to look up the Arctic Ocean and see what its commonly agreed upon boundaries happen to be. But here's a nice map showing you the size and distribution. We have the Pacific over here, Atlantic in between North America and Europe and South America and Africa. You have the Indian Ocean south of India. And then you have the Southern Ocean, which it looks like they've drawn the boundary line at roughly the 50-degree parallel, minus the southern tip of Argentina and Chile down here. And so that's kind of like an arbitrary kind of thing, even with their little bump there. But the Southern Ocean essentially circles Antarctica. They have a nice distribution of the different land masses and the different oceans, which I don't know why they didn't put the Southern Ocean on here, but they have the land areas, the Atlantic, the Pacific, the Indian, and then the Arctic, and they have it broken down by northern hemisphere and southern hemisphere, all the way down to the bottom. So there you go. Wonderful. How does the area of the Earth's surface covered by oceans compare with area covered by continents? 71% oceans, 29% land. Most land is in the northern hemisphere compared to the southern hemisphere. Let's see, actually, let's go back and look at this. Yeah, I'd say you've got quite a bit more land area-wise in the northern than the southern, but not like night and day or anything. Just interesting to think about. So now we're going to talk about salinity, the total amount of solid material dissolved in the water. When we think of salinity of the ocean water, we think of the saltiness. The name kind of lends itself to that. But know that there are other things besides salt dissolved into the ocean water. Every year I like to tell my classes about the amount of gold dissolved in the ocean. There's like a ridiculous amount of gold dissolved in the ocean. If we were to take all the gold out of the ocean, I believe the story is it would be more than all the gold we have left on the land. The oceans are pretty big, but gold is non-magnetic and not really chemically reactive a whole lot, and so there's no good way to do that. You can't do like a physical separator of the gold and take it out of the ocean. And by the time you mix it up with chemicals and like extract it and refine it, you've spent more money than the gold's actually worth. And so it's not anything anybody's trying to get out right now or anything, but there's a lot of gold dissolved in the ocean, apparently. It's a big deal. So when we talk about salinity and the things that are dissolved in the ocean, it's typically expressed as a percent, not as a normal 100% though, because they're so small. The dissolved substances in seawater are such small quantities that it's expressed in parts per thousand. So not like a percentage of 100, but a percentage of 1,000. Most of the salt in seawater is sodium chloride, which is the normal salt that we think of. So if you have 1,000 grams of water, 965 of that is going to be actual H2O, pure water. 35 of those grams, or 35 parts per thousand, is going to be your actual salts. Now, of that, most of it is sodium chloride. About 85% is going to be sodium chloride. You do have some other constituents that are going to be your positive ions and your negative ions. So you have calcium plus 2, you have potassium, magnesium, you have a sulfate, sulfur and oxygen together, and then a couple other minor things like strontium and barium. Is that barium? Yes, barium, and then, no, bromine, sorry. Barium's Ba. Bromine, and then carbon. And so you have lots of different things dissolved into the ocean water, but the vast majority of it is going to be your sodium chloride. So just remember that if they give you in parts per thousand, it's going to be 35 parts per thousand. If they give it to you in a percentage, it's going to be 3.5%. Now, sources of sea salts. Where do the salts come from? We have two main sources. One's going to be chemical weathering of your continental rocks. As weathering happens, as water falls, and that water slowly makes its way down into the oceans, it's going to carry with it little dissolved pieces of your minerals. And a lot of that is going to be your sodium chloride. And so your dissolved minerals from chemical weathering are going to be added to the water column, and they're going to contribute to your salt. The other part of that is going to be volcanic eruptions, whether they're subsea volcanic eruptions or volcanic eruptions that spew gas into the air. Much of that is going to end up in the ocean eventually, whether it falls directly in there or runs off through more chemical weathering and erosion. It's slowly going to make its way into the ocean. Another thing that I mentioned in the last class, if you've seen these, I actually had a video that I played for Other Than Space, but the black smoker stacks at the ocean floor. Has anybody seen? Yeah. It's basically like a little volcanic vent that just spews out this really black, super mineral rich water. It wasn't too long ago, we didn't even know they existed. And then once they were discovered, we now think that they're all over the ocean floor, all along the mid-Atlantic ridges. And so there's quite a bit of those contributing to the salinity of the ocean water as well. The composition of the seawater has to be relative, or has been relatively stable for millions of years. The material that's in it gets removed as rapidly as it gets added, and so it kind of stays stable. There's animals that use it to build their shells and use it as sustenance. It settles to the bottom of the ocean floor. It gets chemically combined and reacted with other things, but there's always more being added. So it stayed pretty stable for quite a while. So what processes affect seawater salinity? We essentially have two: addition of fresh water and removal of fresh water. To add fresh water, you can talk about rain, precipitation directly into the oceans. You can talk about runoff from the continents, which can carry more sediments to it, but a lot of it does contribute more fresh water than it contributes to sediments. Runoff coming from a stream or a river is not going to be nearly as salty as the ocean water already is. And so it's generally more fresh than the ocean water you have. And then melting of icebergs and sea ice is going to contribute more fresh water to kind of reduce that salinity and bring it down. The opposite is going to be removal of fresh water. If your evaporation is more than your precipitation, your water level is going to go down, the salt will stay there, and you will get more salinity. Or the opposite, formation of sea ice. If you enter into an ice age and you have ice forming, that ice is going to take water out of the water column, but not salts really. The ice isn't going to be like salty ice. It's going to be more fresh ice. So, and your latitudes and seasons can change the salinity as well. They have a nice map here that shows you the salinity changes from the North Pole all the way down to the South Pole. Note that at the equator, you have a dip in salinity where your temperature is the highest. One of the reasons for that is the equator, you have the most rain. You have the most like fresh rain that's happening over the oceans quite a bit. And so that's going to bring your salinity levels down. Same thing towards the poles. You have a lot of ice activity that's happening there. And so sea ice and glaciers and icebergs are constantly being added to the water. And so that's going to help bring your salinity down, along with just the general chemistry differences that are happening at different temperatures. So now, what are the two primary sources for elements that comprise the dissolved components of seawater? Chemical weathering and volcanic eruptions, whether undersea or on land, are going to add to your salinity of your ocean water. Now, we're going to go through a couple different chemistry kind of takes on the oceans themselves. So we start off with the thermocline. This is temperature variations. Thermo meaning heat, cline meaning slope. And so we're going to look at the slope of different heats as you go down with depth in the ocean. If you've ever been swimming in the lake on a hot summer day and you get out to the area where the upper water is nice and warm, but your feet get really cold in the cold water, have you felt that? It's really nice. It's nice on a hot day. That's because of the thermocline. That sun energy doesn't get down to 4 or 5 feet down, and your feet get that nice cold water, and it feels wonderful. So here's a representation of the thermocline in the ocean. You can see at the surface, you're up here near 20, 24 degrees Celsius, and that as you go down, you experience this thermocline. And the greater depth you get, the colder you get. So at around 1,000 meters depth, you're down near like 4 or 5 degrees Celsius. And then it just keeps going down until you level out around 2 degrees Celsius. Notice it doesn't matter how deep you get. You're not going to get below 0 Celsius because that's where ice starts to form. That's not really a temperature you're going to reach in the super deep depths. It'll get really close to it, but it won't get down to 0 degrees Celsius. In the higher latitudes, you get a lot less sunlight, and you have different physical processes affecting your surface temperature, and so you don't get that warm surface temperature. It's just a straight line for your temperature line, so there is no thermocline. They call it an isotherm, same temperature or same heat. Now, instead of temperature, we're going to look at a couple different ones. We have density variations, which they call pycnocline. Density is pycno. Cline is going to be your line as well. So density variations can be influenced by salinity. The more dissolved solids you have in your water, the more density you're going to have. That just helps add to the weight of your water and the density of your water. It can be influenced by temperature. The hotter the temperature, the more your atoms spread out and become less dense. We see that with anything. Hot air rises, hot water rises, cold air and cold water sink, because the higher the temperature, the more your atoms are moving, the more spread out they are. The colder your temperature, the less they're moving, and the closer they're packed together, which increases your density. So these are going to be opposite. If you increase the temperature, decreases the density. If you decrease the temperature, increases the density. So that's influenced by temperature. And then finally, influenced by depth. Think again of how close your atoms are packed. The deeper your water is, the more pressure you have, and the atoms get squeezed together, which is going to increase your density and make it more dense and more dense as the further deep you go. So increased depth, increased density. This creates a pycnocline, which is a rapid change of density with depth. It's not present at the high latitudes, just like the thermocline is not present at the high latitudes. So they show you that again. Where's this lady floating?
Dead Sea.
Yes, the Dead Sea. Where's the Dead Sea?
Mediterranean, I don't know.
Yeah, well, close. It's in Israel. And actually, like, I knew it was in Israel, but I went to the map and I'm looking for the Dead Sea and it's just not there. And then finally I see the words Dead Sea, but there's literally no blue part on the map to show the water. So it must be really, really small.
We have water and sand from the Dead Sea in our house.
Nice. And the name kind of goes along with what's happening here. The Dead Sea has had a environmental change where it was getting a lot more water input, and now it has much more evaporation than it has input. And so what's happening in the Dead Sea is you have what water does come in is highly salinated and has a lot of minerals, but you have more evaporation than you have input. And so the Dead Sea is slowly kind of declining, which is one of the reasons that kind of leads to its name, not the only reason. But it's also the reason that makes people much more buoyant, is because it's a very high salinity. It also makes it, nice to kind of bathe and luxuriate in if you're in that part of the world. So yes, she's reading a newspaper that's written in Hebrew. And then they show you the pycnocline here. It's kind of the opposite of the thermocline. At the top, where you have more fresh water, you're going to have a lower density. And then as you go down towards the depths, your pressure, your temperature, and your dissolved solids all kind of add to the density and make it more and more dense. At your high latitudes, you're just not going to see that. The water is more of kind of a I don't know. I've been searching for the word all morning. A monolith. I don't know. There's not much variation in the water from different depths. So at the top, you have pretty much the same density as you do at the bottom. Same thing with the temperature. The top and bottom temperatures are roughly the same at your very high latitudes. So now they get into your different layers of the ocean, and they have 3 layers. Your shallow zone, which they also call the mixed zone, your transition zone, and your deep zone. The deep zone is going to be the biggest. You can see the deep zone is pretty much everywhere. In the northern latitudes and the southern latitudes, you don't have that differentiation. You don't have the thermocline. You don't have the pycnocline, and so all your water is kind of the same. So it's only deep zone at the North Pole and at the South Pole. But towards the equator and towards the tropics, you do have that transition zone, which is going to be slightly less dense, slightly higher temperature. And then at the surface, you're going to have your lightest density and your highest temperature, which is going to be your surface zone or your mixed zone. And this is where you're going to have rainwater falling directly into the oceans, which is going to contribute more fresh water. And you're going to have your higher temperatures. And so all of those things kind of lead to this different 3-layer kind of structure happening here. Now, what are the 2 factors that influence density? Which one has a greater influence in surface seawater density? So you have salinity and your temperature. Both of those affect how dense your water is. The temperature is going to have the greater effect. Salinity does come into play, but temperature can kind of override that. So now, how do we see the ocean floor? How do we make maps of the ocean floor? And what's kind of the history of that? So the term is called bathymetry. Bathymetry is mapping the ocean depths and the shape or topography of the ocean floor. And we started doing this in the 1920s with echo sounders. This is your sonar that we use. So if you've ever watched like a submarine movie and you hear the boo, which by the way, if you've never seen Hunt for Red October, the wonderful Sean Connery just passed away. And if you haven't seen Hunt for Red October, I highly recommend it. It's a great film. Not a lot of great like submarine films, but Hunt for Red October is one of them. And let's just talk about Sean Connery, the crazy, he was Scottish, right? The crazy Scotsman who just got hired to play all sorts of other nationalities and never got rid of his Scottish accent. They're like, hey, Sean Connery, will you play a Russian for us? Yes, but I'm going to be a Russian with a Scottish accent. Hey, Sean Connery, will you play a Spaniard for us? Yes, but I'll be a Spaniard with a Scottish accent. That's just me. That's what I'm going to do. I'm not going to get rid of my Scottish accent, even if I could. Yes, I love Sean Connery.
That's my mom's celebrity crush. She's very sensitive.
Yeah, he's a big deal. Multiple James Bonds. He was great. He was great. The Rock. If you've ever seen The Rock, both a terrible and a great movie at the same time. Nicolas Cage will do that to a movie. Yeah, he'll make it great and bad at the same time. Is one of y'all a Nicolas Cage fan or not a Nicolas Cage fan? Yeah. I completely understand that, but yeah, Sean Connery has some great movies out there. So back to bathymetry. I don't even know how I got on that. Oh, submarines. That's why. So echo sounder sonars was invented in the 1920s. The primary instrument for measuring ocean depths for quite a while. We have new technology now that we use, but we still use echo sounders. And basically, your boat has a sound emitting device, usually going to be like a ping. Your higher frequency sounds are going to be able to travel further, but it emits a ping. Boo, it goes down to the ocean floor where it hits the floor and bounces back, just like your echo in like the Grand Canyon. When you yell and it bounces back to you and you hear it. Through scientific experimentation, we know how fast those sounds travel in water. You might have to make some adjustments based on temperature or density, but we know how fast the sound travels in water. So we wait for it to bounce off the surface and come back to us, and we do a little bit of math, and now we know how deep the ocean floor is. And so it started off very simple like that, not a lot of technology, but over the years we've gotten better and better at it. So now today we use multi-beam sonar. This is an array of sounds and listening devices, and it obtains a profile of a narrow strip of the seafloor, which is actually much more detailed than your standard echolocation sonar. This multi-beam sonar is actually how we explore for oil and gas, also not just the seafloor. And so let me actually go to it right now. They have a ship, and behind the ship, they pull this sonar producer. Now, if you're just looking at the seafloor, it's probably just going to make sounds in different frequencies that are going to bounce back up. If you're looking at like an oil and gas array, this will actually be the receiver back here, and you will have a instrument on the boat that releases a large air burst. And that air burst produces sound enough that it goes down to the seafloor and doesn't just bounce off the seafloor. It does that, but it also penetrates the subsurface and gives you some seismic waves beneath the surface where you can see a profile of the different rock layers underneath the surface. And so that's rather advanced technology that we're using today. Along with that, we have satellite altimeters, which are satellites equipped with radar to measure variations in the sea surface from space. If you ever go on to like Google Maps and look at the oceans, or Google Earth and look at the oceans, you can see these really detailed maps of the subsurface of the ocean, and that's how they get that through satellites. So it's actually pretty good stuff. You can see like the Mid-Atlantic Ridge in all its glory and all the different details there. So they have a nice map here giving you some of this. You can see the Mid-Atlantic Ridge. You can see some of the ridges surrounding the Pacific Plate. You can see the Hawaiian chain that turns into the Emperor chain and goes up towards the tip of Russia and Alaska. There's all sorts of stuff that you can see, but we've got quite a bit of information about the subsurface of the ocean through lots of different sonar and radar kind of capabilities that we've developed. Now, we're going to talk about the provinces of the ocean floor, the different types of ocean floor areas that we have. Our three major ones are going to be your continental margins, your ocean basin floor, and your mid-ocean ridge. And we will split the continental margin into smaller little subsections there. But your continental margins can have two different parts, passive or active. We should kind of get through both of those today. Your ocean basin floor is essentially your deep, deep ocean, which they call the abyssal plain. Very deep, not a lot of life relatively going on there. You do have some underwater volcanoes that we call seamounts. And then obviously we spent quite a bit of time talking about your mid-ocean ridges and your rift valleys there. So we're going to focus mainly on the continental margins, especially today. So here's a nice profile of what happens with your continent. And to start off, we're going to talk about passive margins. In a plate-to-plate connection, which this is oceanic plate, this is the North American continental plate, where there's no activity going on, your continental plate can actually come further out into the ocean. And so seeing this, we kind of think, the continent ends where the water begins. But that's not true. Our continental plate comes far, far out into the Atlantic Ocean before you really have that drop off and your oceanic plate begins and you have that deep, deep ocean. And so you can kind of see that here. Your continent actually ends, like your actual land ends right at the edge of this. You have a gently sloping continental shelf, which goes down to your continental slope and your continental rise, which is all part of the margin. We'll go over these in a second. Your deep ocean basin is your deep, deep ocean. You have a couple underwater volcanoes here that they show with little spikes. Then you get into your mid-ocean ridge, which kind of rises up, which is why we call it a ridge. So it gets higher and higher until you get to your actual splitting center here, which is your valley. Then it just repeats itself on the other side. So your ridge goes down, deep ocean basin, then your continental margin where you come up the rise to your continental slope and your continental shelf. You can see some continents are going to have bigger shelves that extend further out into the ocean than other continents. We have a nice big one over here on our eastern seaboard where the western coast of Africa doesn't really have a super large one. But both of these are kind of passive margins. There's not a lot of stuff going on here. So as they talk about a passive continental margin, just know that your plate boundaries here don't have a lot of action going on. We do have a plate boundary between oceanic and continental crust here, but there's no subduction, there's no spreading, there's no transform faults going on, which is why in general, our two coasts are very, very different. On the west coast, up in Oregon and Washington, we have volcanoes, we have earthquakes. We talk about earthquakes all the time in California. We have no volcanoes on the eastern seaboard, no earthquakes really to talk about on the eastern seaboard. There's all sorts of movies about Los Angeles falling off into the ocean or suffering like the 10.0 earthquake. That never happens to New York. No one talks about Florida like falling off into the Gulf or anything because it's a nice passive continental margin where really, to be honest, not a lot is happening. Geologically, they're all pretty safe over there. And so that's what a passive margin means. Very little volcanism, very few earthquakes, not a lot of action going on. So now to break down your continental margin, we have three different areas here. We have the continental shelf, and these terms kind of help you visualize it. The shelf is going to be relatively flat. So think about, for my lake people, when you go to the lake, and not all lakes do this, but you go to the lake and you get out to the water and you start to walk, and you walk like 5-10 feet out and you haven't even got up to your knees yet. Yeah. And it just goes really slow, and then all of a sudden you take that last step and you like almost fall all the way in, and it's like above your head. That's kind of the continental shelf, is that real shallow part. It extends out further than you usually think. But when the shelf ends, you really get that steep, steep drop off. So it is gently sloping. You are getting deeper as you go further and further out. It's just kind of an extension of the continent that happens to be underwater right now because of our current ocean levels. There's a lot of oil and important mineral deposits out there. So if you think about like oil drilling in the Gulf, that's what they're on there, is that continental shelf. Some areas have extensive glacial deposits. Most consist of thick sediments accumulated over time in the very shallow water. Where the shelf ends, you get to your continental slope. This is going to be relatively steep. It's going to mark the edge of the continent and the beginning of your oceanic crust. So that's the slope there, and I think they're going to show us a picture in just a second. Now, at the edge of your slope, going down into what is called the continental rise, we have a couple features, and they'll show us this on a picture in the very next slide. Submarine canyons, this is going to be just like a canyon that we have on land, like the Grand Canyon. It's going to be because water's moving in a kind of a stream underwater. Sometimes it's an extension of like a river. Sometimes it's just due to tides and the movement of the water. But as you have these canyons, that edge can be worn away. You can have erosion kind of happening even underwater. And so when you have that, you have these little underwater landslides, which we call turbidity currents. The turbidity currents move a lot of sediment from up on the shelf down the slope to the bottom of the slope, which is called the continental rise. And when they settle and become rocks, we call them turbidites. Turbidites are actually a really hot oil and gas play right now. They're difficult to find. They're very complex, and you never know what you're going to get. But oil and gas companies do look for turbiditite complexes to kind of drill into. So here's an image of how this is. And this is off of the East Coast again. You have your continent, your freshwater runs off here, your nice continental shelf, and then they have the canyons right at the edge, because this is actually a very, very steep drop off. And so you're going to have sediments, just due to gravity, are going to want to fall down this slope once they build up enough. And so when you get these underwater landslides, those are called the turbidity currents. When they break off and slide down, they form these submarine canyons. And when they fall all the way down and kind of settle out, these deep sea fans are made up of rocks they call turbidites, kind of like the turbulence in water. They all kind of get mixed up and churned up. So these are your three different areas of the general continental margin. You have your shelf, which is nice and flat, your slope, which is very steep, and then after the slope kind of starts to level off, this gently rising thing is called the continental rise. Once you get past that, you're in the deep ocean. This is the abyssal plain, your deep ocean basin. So, nice. Now, passive continental margin features. We've kind of gone through these. The continental rise is the last one. Found in regions where trenches are absent, your continental slope merges into a more gradual incline, and at the base of the continental slope, you get those turbidity currents, which deposit the turbidites in your deep sea fans. Now, here's just a map to kind of show you that some areas have that large continental margin. Some areas do not. Your continent really just drops off immediately into your deep ocean, especially wherever you're going to have subduction. If your oceanic plate is kind of being subducted underneath your continent, you're not going to have the chance for that continental margin to extend further out. It's all just kind of going to be abruptly joined together. So in active continental margins, instead of the slope, the rise, and the shelf, you just have the deep ocean trench. So your continental slope descends abruptly into a deep ocean trench, located primarily around the Pacific Ocean, because that's your ring of fire where you have most of your subduction happening. You can have the accretionary wedges, which you talked about before. It's like the mud being kind of scraped off your boot as your oceanic plate gets subducted underneath your continental plate. They do point out that some subduction zones don't have a lot of sediments, so they don't get big accretionary wedges, but most of them do. So here's just another picture of the turbidites and that continental slope / shelf. So here's your shelf. You can see this one kind of aligns with freshwater running off the continent. You have a bay here, you have a river coming out, and as it comes out into the ocean, it's going to deposit a lot of sediments here. If the sediments build up too close to the edge, they're eventually going to fall down, and you're underwater kind of landslide. And a little thing that I didn't know for quite a while, even though we have satellites, that's not the main way we get communication from one place to another. We run cables all the way across the ocean floor from the United States to Europe and from different continents to continents. They're really big cables. We spend a lot of money doing it. And one of the things that has kind of led us to understand a little bit more about turbidites is every time we have one of these landslides, not every time, but if there's a cable nearby, this landslide will cut that cable. It will break it. It will cause interruptions in communications, and we will have to go out and repair it over top of it. And so I didn't really understand that we were actually like doing that and running deep sea cables, but yeah, there's a lot of them. And I think one of the things they're looking at next is like fiber optic cables across the ocean, which would be pretty expensive, but we'd be able to move massive amounts of information. You can move stuff through satellites. There's just not a whole lot of satellites to move massive amounts of information like that, and it would go a lot faster in a cable where you can move huge amounts of information. So if you think about like banking purposes, they're using those cables. Banking's I don't know about like telephone calls, but we have a lot of information exchange with Europe and all the other different continents. And so, yeah, it seems like an impossible thing to do, but we do impossible things all the time as human beings. And I guess we'll leave off here. How much time we have left?
5 minutes.
Like 5 minutes?
3 minutes.
We'll leave off here. I don't want to get too far ahead of the other class because that messes with my brain a little bit. But we got through plenty. 33 slides. We'll finish this up tomorrow and be done with this chapter. So for Mr. Ian at home, my only online student as of right now in this class. I got one more, but have a nice day, sir. I hope you watch the video.